Okay, now we're going to talk about induction on lists. So the reason why induction on lists work is because the integers and lists are both defined in a recursive manner. So every integer is either equal to 0 or some integer plus 1. Similarly, every list, loosely speaking, can be considered to be an empty list or some element A bolted onto a list with A's in it. So a list is either empty or it's an element with an element tacked onto a list. So it's a recursive definition. And when you have a recursive definition, that means we can usually do induction proofs on it. So here's how list induction is formally written for lists. So just like before, you have to prove for the step case. So you have to prove P is true, in this case, for the empty list being the base case for lists. I have to show for any list XS, if it's true for the list XS, then it's true for the list X cons XS, where X is any new element. So they have to show it's true for any new element X, P of X cons XS. When I say cons, that's the colon operator. The cons operator is what allows you to attach an element to a list. Okay? So base case is prove it's true for the empty list. Step case is assume it's true for some list XS, and then prove it's true for any new list X cons XS, where X is an arbitrary element. Okay? And if both of those are proven, then we have for all lists XS, P of XS. Okay, so let's do an example. Here I've written the definition of concatenation, and I've changed the name of the variable so that way we don't get confused when we're referring to XS as a specific list or XS in the definition of the function. So suppose I want to prove from this definition that for any list XS, XS concatenate an empty list is equal to XS. Okay? It looks like you can trivially do it, but we don't have a definition when the first list is not empty and the second list is, right? It doesn't immediately follow from A1 that this is true. So we have to prove it via induction. Okay? So we prove the base case. And the base case here is going to be XS is the empty list. So we need to prove that empty concatenate empty is equal to empty. And this is not too bad. On the left-hand side is empty concatenate empty. Look at the definition of concatenation. Empty concatenate PS is the same PS. So this empty here is going to be my PS. So this is equal to empty by rule A1, which is equal to the right-hand side. Okay, so that was a short one-liner. So base case is proven. Now I need to prove the step case. So for the step case, I assume the statement to be true for some ys, so for some xs equals ys. So I'm assuming that ys concat empty is equal to ys. I need to prove for any new variable y, so I need to prove for any new element, I should say, for any new y cons onto ys, concat empty, is equal to y cons ys. For any choice of y. So I'm going to let y be arbitrary. Okay, and we need to prove y cons ys, concat empty is equal to y cons ys. And this assumption of ours we should denote by IH because it's our inductive hypothesis. Okay, so let's do the proof. How do I evaluate this? I look at the definition of concatenation. If I have Q cons QS concatenated with PS, then I can take the Q out the front and concatenate what's left over. So I can do that here. I can take the Y at the front. So this is the same as, so the left-hand side, which is this term here, is the same as Y cons onto YS concat empty list by rule A2. And then I look at this term here and it perfectly matches my inductive hypothesis. So I can apply the inductive hypothesis here and I get Y cons YS concat empty is this YS by inductive hypothesis, and that's equal to the right hand side. Okay, so I proved it true for the base case, the empty list. I assumed it to be true for some arbitrary list and proved it was still true for that arbitrary list with some arbitrary element tacked on the front. Therefore, it's true for any list. So therefore, for all XS, xs concat empty is equal to xs. And proof is done.